Today we are covering section 2.2, the algebra of functions. Here are our objectives: to find the sum, the difference, and the product and the quotient of two functions, determine their domains, and then also figuring out the difference quotient for a function. So getting into it, we're going to assume that f and g are functions and that x is in the domain of each of those. Then we say f plus g of x is the same thing as f of x plus g of x. I like to think about this side as thinking about how do we actually represent functions. What does f really mean? Well, if we have a function f, typically we have something like f of x equals something happening to x. So say, for example, we have x squared. Then I like to think about f as the operation of squaring, right? It's like f of x represents x squared. That means that we need to square our x value. And so f is that operation of squaring the x value. So when we think about what we have on this left-hand side here, f plus g, it's almost thinking like, well, what happens if we add the operations of our functions? And it turns out that's the same thing as if we just take f and then evaluate it at x, and we take g and evaluate it at x, and we take their sum. So instead of having to try to figure out how do we add operations like this, then apply it to x, we have this nice rule where we can just apply f to x, apply g to x, and add them. So you're going to find the right-hand side is kind of the natural choice of what you do when you want to look for anything on the left-hand side. But this is actually a rule that's happening here that allows us to do those kinds of operations. So let's get into it. Let's say that we have an f of x that equals x plus 1 and a g of x that's the square root of x plus 3. Then you want to find each of the following. So we want to find f plus g of x first. Well, f plus g of x in this weird notation is the same thing as f of x plus g of x. Well, f of x is x plus 1. So we're really looking at x plus 1 in place of f of x, and then square root x plus 3. So we basically just take, let me fix this. We just take our f and we add g, and we just stick them together in one line. And that is it. That is all we have to do here. So we do the natural thing of just add whatever we have for f to whatever we have for g, and we move on. Now, when looking at part B and we want to evaluate this at 6, we just plug in 6 for x. So f plus g of 6 is 6 plus 1 plus the square root of 6 plus 3. Well, that's 7 plus the square root of 9, which is 10. 7 plus 3. So we evaluate the function at a given x value the same way as we did before. Now let's see what happens when we try to plug in -4. So we have f plus g of -4 is -4 plus 1 plus the square root -4 plus 3. So -4 plus 1 is -3 plus the square root -4 plus 3 is -1. Oh, but we can't do that. We can't do the square root of -1, which means f plus g of -4 does not exist because of this right here. That's not okay to have. All right, so sometimes we can have x values that can be plugged into one function, such as -4. It was fine to plug into f, but you can't plug it into g. And so therefore, when we add f and g, the same rule applies. You still can't plug it in. Okay, so sometimes we have values that don't exist. All right, that's what those look like. So now, whenever we want to think about the domains of these functions, as you saw, -4 was not in the domain of f plus g. Because it was not in the domain of g, naturally then, we look at in general, that is true. So the domain of f plus g, f minus g, and f times g is just the intersection of the domains of f and g. And then the domain of f divided by g is the same idea. It's the intersection of the domains of f and g, but you want to take out any x values where we get a 0 for g. If we get a 0, then in the denominator, that's bad. We can't do that. So we just always have to check for that case if we ever have an f divided by g kind of situation. So let's see some examples. Given that f of x is x squared minus 4 and g of x is the square root of x plus 2, find each of the following. And we're going to walk through these step by step on the next few slides. We're going to look at f plus g, f minus g, f times g, f divided by g, g times g, and then the domain of each of those. So starting off with f plus g, let's just try to write it down. So f, which is x squared minus 4, x squared minus 4 plus square root x plus 2. There's nothing we can simplify here. That's actually it for this one. F minus g looks kind of similar. X squared minus 4 minus the square root x plus 2. Again, no like terms that we can get rid of. We can't get rid of that square root on the x plus 2, so we're stuck. Moving on to C, where we have f times g. And we want to make sure we simplify our answer. I'll show you what I consider the simplified answer here too. So if we have f times g, we're looking at x squared minus 4 times square root x plus 2. And the only way that we can simplify this a little bit is to write it x squared square root x plus 2 minus 4 square root x plus 2. Because the square root x plus 2 can't be broken up, but it can be distributed to those two terms. Moving on to part D, we want to look at f divided by g of x. So this gives us x squared minus 4 divided by the square root x plus 2. And that's it. We just wrote that one down. Now, what if we have g times g? Well, that would be the square root of x plus 2 times the square root of x plus 2, which is really the square root of x plus 2 squared, which gives us just x plus 2. Moving on to part F. To figure out the domains of f plus g, f minus g, fg, and f divided by g, let's first write down the domains of f and g themselves. So the domain of f, let's start with, well, f isn't a fraction and it's not a square root, so it's no special case that we need to be extra careful of. Essentially, the domain is negative infinity to infinity. The domain of g, well, that x plus 2 must stay positive because we do have a square root here. So we need a positive x plus 2. So let's do that to the side. We want x plus 2 to be greater than or equal to 0. So which means x needs to be greater than or equal to negative 2. Just subtract 2 from both sides. So then the domain of g is everything where x is greater than or equal to negative 2. So things like negative 1, 0, 1, 2, and on and on and on upwards. Which means we start at negative 2 and we go on to infinity. Parentheses with the infinity, and it's okay to include negative 2. So there's our domain of g. Well, that means that we want to just think about the intersection of these two domains. Well, f is everything, so g is really what sets the domain. And we remember from the beginning that f plus g, f minus g, and f times g has the domain of the intersection, which is just -2 to infinity. For f over g, we need to make sure that g does not equal 0. So essentially, we can't have the or equals 2 case here, because if x equals -2, then g of x gives us 0. So that means for f divided by g, the domain is parentheses -2 to infinity. Essentially, we don't want to include the -2 here, because again, when x equals -2, we get a 0 for g of x, and that's bad for the denominator. So we just leave out -2, we take the rest of the domain, and we've got it. So now let's move on to another example. So given that f of x is 5 over x plus 1, and g of x is 1 over x minus 4, find each of the following. The domain of f plus g, f minus g, fg, and f divided by g again. And then we're actually going to find f times f and f divided by g. So starting with part A, let me see if I have another slide here. Yeah, I thought so. So starting with part A, the domains of f plus g, f minus g, fg, and f divided by g. Let's first find the domain of f. Well, f is a fractional function, which means we need to be worried about 0 denominators. So we want to know when x plus 1 equals 0, and then not include that x value. If we subtract 1 from both sides, we get x equals -1. So the domain of f is everything but -1, or -infinity to -1, union -1 to infinity. Everything but -1. Okay, the domain of g. Well, g is also a fractional function. We want to know when x minus 4 equals 0. If we add 4 to both sides, we get x equals 4. So we want to make sure to not include 4. So, -infinity to 4, union 4 to infinity. Okay, well that means that the domains of f plus g, f minus g, and fg we can write down immediately. They all have the same domain. And we want to basically do the same idea that we have from f and g. We want to leave out -1. We want to leave out 4. So that's -infinity to -1, union -1 to 4, union 4 to infinity. We just build it by basically skipping over -1, skipping over 4, and that's the intersection of those two different domains. And then when we think about f divided by g, we just want to know when g equals 0. So for the domain of f over g, does g itself equals 0? Let me say g of x. G of x equals 0. Well, you could put it in your calculator, and look at the graph is one option, but also just look at the function. When I have 1 over a number, is that ever going to give me 0? Well, no, right? Because even if I have a 0 down here, it says does not exist. I never actually get this function equal to 0. So, no, that never happens. Which means the domain of f over g is the same as the domain above. -infinity to -1, union -1 to 4, union 4 to infinity. It's the same as the one above. There's no zeros to worry about, essentially. Now we want to find ff and f divided by g. Well, f times f is just going to be 5 over x plus 1 times 5 over x plus 1, which is 25 over x plus 1 squared. And to me, that's the simplified answer. Now if we want to find f, so this is f times f. If we want to find f over g, well, let's write that out. 5 over x plus 1 divided by 1 over x minus 4. Try to use a really big divided by bar in the middle there. Kind of helps keep your fractions organized. Well, when we have a fraction divided by a fraction, we always multiply by the reciprocal. So we take the first fraction, we multiply it by the reciprocal of the bottom fraction, and we get 5 times x minus 4 divided by x plus 1. Right? So that's what it simplifies to. All right, moving on. So given the graph to the right where we have f and we have g, what is the domain of f, the domain of g, and then the domain of f plus g? So we need to get used to picking this up off of a given graph. So the domain of f is the blue line, and the domain is all of the x values that it covers. So I see it start here at 0, and it finishes at 9. And notice that it is a closed circle on both. So we use brackets, 0 to 9. Okay. Now looking at g, g is our green line. G is going to go from 2 to 11. And again, closed circles on the endpoints, so it covers 2 to 11. Okay, and then the domain of f plus g, well, that's the intersection of the two domains. So the intersection of f, the intersection with the intersection of g. That's basically saying, well, where do they overlap? Well, they overlap from 2 to 9. Right? 0 and 1 is not in the domain of g, and then 10 and 11 is not in the domain of f. Therefore, their intersection spot is just from 2 to 9. So from here to here, we have both functions showing up, right, across that entire space. You'll have a couple of these on your homework. So why is this kind of thing useful? Well, it's actually used in economics all the time. Because in economics, typically we say for an item X, we denote revenue by R of X, we denote cost by C of X, and we denote profit by P of X, which is the difference between revenue and cost. And as a reminder, revenue is all the money you're bringing in total. Cost is what you might have spent on that item. So profit is what you actually get to keep. The money brought in minus the cost of those goods gives you your profit. So it's actually very important that we understand how to add, subtract, multiply, and divide functions. So let's see an example. Suppose x represents the number of apples sold at a grocery store. The R of x is 25x minus 0.3x squared, and C of x is 3x plus 10. Find P of x, so our profit. Find R of 90, C of 90, and P of 90. And then using a graphing calculator, graph all three functions, R, C, and P, and in a certain viewing window. So this 0 to 100 will be our x-axis, and the 0 to 550 will be our y-axis. Let's go through this together. So P of x, we have R of x and C of x at the top. P of x is, of course, R of x minus C of x, which is 25x minus 0.3x squared minus, parentheses here, 3x plus 10. And if we were to simplify this a little bit, we have 25x minus 0.3x squared minus 3x minus 10, right? We distribute that negative to both terms. So now we can combine a few like terms. We'll have negative 0.3x squared. And we have a 25 and a minus 3x. So that's plus 22x minus 10. And this is what P of x looks like. Nice. Okay, moving on. And let's write that down real quick. So that P of x was negative 0.3x squared plus 22x minus 10. Let me just check my work there. Yeah, that looks good. Okay, so we want to find R of 90, C of 90, and P of 90. So R of 90 is 25 times 90 minus 0.3 times 90 squared. And if I get my calculator out, because no, I cannot do that in my head, I have, let's see, negative, nope, not this one, 25 times 90 minus 0.3 times 90 squared, which gives us negative 180. Okay, C of 90 is 3 times 90 plus 10. 3 times 90 is 270 plus 10, so that gives us 280. And now to figure out P of 90, I actually don't even need the function from the previous slide, right? I can do R of 90 minus C of 90 as values. So that's negative 180 minus 280, which gives us negative 460. Let me just check with my calculator. 460, negative 460. So we're actually losing money on these apples, right? Because it's a negative 460. All right, moving on. Using a graphing calculator, graph the three functions in the viewing window. So let's jump over to our graphing calculator and graph all three of these. All right, go to our y equals, and we want to look at 25x minus 0.3x squared, enter. And then we have 3x plus 10, enter. And our profit function was oops, there's my mouse. Negative 0.3x squared plus 22x minus 10, enter. And the problem asked us to put it in a certain window. So if I go to my window and the x minimum was 0, the maximum is 100. And the next line tells us, well, how do we want to count by on our axis? I don't want to count by 1. I'd end up with 100 tick marks on my x-axis. So let's count by 10. Our y minimum is 0. The y max is 550. And for a y scale, let's count by 25s. And we graph it, and there it is. We see all three functions. Okay, going back to the slides. So we saw what it looks like to graph those. You'll actually see a problem in your homework that gives you a window like this and asks you to pick which graph it is. So, moving on, our next topic we want to talk about is the difference quotient. So the difference quotient is actually an average rate of change formula, and it looks like this. It's f of x plus h minus f of x divided by h. And why we care about it is because it's actually the slope of what we call a secant line. A secant line is where you take a curve like this f here, and you pick 2 points and you draw a straight line through it. And if you're trying to find the slope of that line, because maybe it's helping you approximate something about the curve, we would have to do change in y. So that's f of x plus h minus f of x. And then we'd have, on the bottom, we'd really have x plus h minus x which gives us h, and that's how we get this. But this really is a change in y over change in x between these 2 points. Basically, you want to think of the plus h by x plus a little bit. Okay, so it's like we're taking our current input, we're just going to add a little bit to it and see what happens. That's what the difference quotient is doing. It's very useful in calculus. You'll see this a lot if you go on to calculus. So for now, you just have to get used to working with this formula. So let's get some practice in. Let's say f of x is 2x minus 3. The first thing I always want you to do is find f of x plus h. And plug in, everywhere you see an x, you plug in x plus h. So that's 2 times x plus h minus 3. To simplify this, it's 2x plus 2h minus 3. So now, excuse me, if I try to write out the function f of x plus h, let me give myself a little more room here. F of x plus h minus f of x divided by h. Now we can plug these things in a little easier. So I have 2x plus 2h minus 3. That's what we found for f of x plus h. Now I subtract f of x, 2x minus 3. And this whole thing gets divided by h. Now let's simplify a little bit. We got 2x plus 2h minus 3 minus 2x plus 3 all over h. I distributed my negative on that last step. Well, now if we combine like terms, notice I have a plus 2x and a minus 2x, so those two go away. I have a minus 3 and I have a plus 3, so those two go away. So what I'm left with is 2h over h, which is just 2. And that's it. We've simplified this difference quotient. Now let's do the same thing for this function. Remember that the difference quotient is f of x plus h minus f of x all over h. So let's find f of x plus h first. That's negative 1 over 15x plus h. Okay. Negative 1 over 15x plus 15h. All right, let's stick it into our formula and see what happens. F of x plus h minus f of x all over h. Well, that's negative 1 over 15x plus 15h minus negative 1 over 15x divided by h. So this is where things get a little bit tricky. I have to try to subtract these two fractions. Anytime we need to subtract two fractions, we need a common denominator. So to find our common denominator, it might have been easier actually. I'm going to take this first term back a step. Rather than distributing my 15, I'm going to leave it as 15x plus h. All right, that's what it originally was written down as. Let's leave it there. It'll actually be easier to see our common denominator. So our common denominator is a product between 15x plus h and 15x. I don't need 15 in there twice, but I certainly do need an x plus h term and an x term. So my common denominator here is actually going to be 15x plus h times x. And then, remember, this minus and negative becomes a plus. And then again, my denominator, to have a common denominator, is 15x plus h times x. That way, both my first term goes into that second term. My first denominator essentially goes into the second denominator by just multiplying by x. And my second term, my second denominator, I'll say, goes into the common denominator by just multiplying by x plus h. So on top then, to make a 15x plus h turn into 15x plus h times x, we have to multiply the top by x as well. So we have a negative 1 still from before, and then we have a times x. Similarly, if we want to turn 15x into 15x plus h times x, we need an x plus h on the top. And all of this is still divided by h. So I know it's tricky, but we've just made common denominators between our two fractions. We can actually add them now. So from here, we get negative x plus h, right? I can add my numerators, divided by 15x plus h times x, all over h still. So now I have a fraction over a number, we'll say, right? So now we got to multiply by the reciprocal. And remember that this h is h over 1. Okay, so now we have, well, let's think for a second, make our lives easier. We have a negative x, and we have a positive x. Let me get my pen turned back on. Not sure what happened. We have a negative x, and we have a positive x. So we just have an h left, and then we have a 15x plus h times x. Now we're going to do that, instead of dividing by h over 1, we're going to do times 1 over h, multiplied by the reciprocal. Oh, but now I have an h in the numerator, and I have an h in the denominator. So now this simplifies to 1 over 15x plus h times x. Whew, so that was a lot of work just to get to this step. You might want to order it this way on your homework. Put the x and then the x plus h, just in case Pearson's a little bit touchy. I would keep this as your simplest form. But that's it. That's the difference quotient for this fractional function. And so that's it for today, everybody. Thanks for watching the video. And as always, reach out if you have any questions.